All right. I'm here to kind of deliver a quick little message on how pH kind of affects you day to day, and maybe not your own personal daily life, but what pH really means to kind of the world and what we're doing. So I thought this was the best way that I could share some information, talk about a process called acidification, maybe help you understand that, and then at the same time appreciate a little bit more about what you've been learning so far. So ultimately, I want to talk about coral reefs here a little bit and a process again called ocean acidification. So here we go. We're going to start out with coral reefs. So you guys know about coral reefs. You've seen all the movies and stuff like that. Coral reefs are a very, very diverse community. It's where about 80% of the ocean's fish and invertebrates come to reproduce and set up like little nurseries for their offspring. It's a huge nutrient-loading area of the ocean. Most of the ocean doesn't have a lot of nutrients in it. These shallower water areas are usually teeming with nutrients and provide kind of the backbone of the ecosystem of the ocean. Coral reefs, very, very diverse. They've been studied for many, many years. Really cool colors in them and patterns and things like that. If you look really, really closely at a coral, the concept is that those corals are made up of little tiny organisms called polyps. Polyps are these guys right here, and you're talking about something that's usually about half the size to maybe a fourth the size of your fingernail, like pinky fingernail. They're really, really small, and they typically only come out at night. Usually when you think of coral, you only think of like the rock-hard substrate that they live on. You usually don't see these polyps during the daytime. But polyps are kind of an interesting little animal. They're a single organism. They're an animal themselves, which is kind of interesting. They have a couple different really very unique lifestyle pieces about them. So first of all, that's what's really unique and kind of crazy about them, and I find absolutely fascinating, is the fact that these polyps, when they start out as a polyp, and forgive the drawing, I'm going to try to do my best here. It's kind of hard to do this on here. But the polyp is sitting there, and it's got its little tentacles kind of waving around up in the surface of the water, up in the water column. And they've got a mouth here in the middle of them. And then they've got this little cavity down in the middle of their body. And you can see the mouth here, and you can see little tentacles. And those tentacles are usually lined with stinging cells called nematocysts. And those are what cause all the little pain from like bumping into coral while you're snorkeling and things like that. So ultimately, those polyps, when they get food, they bring in food, so they sting their little food, their little prey, which are like little tiny flecks of food out here in the water, usually little tiny microinvertebrates and things like that. They'll take those bits of food in, and they'll digest it. And what's really weird about their digestive process is that when they get done digesting, their digestive process pushes that food back out of their mouth. So their mouth actually serves as their stomach and their anus at the same time, which is really disgusting. And what they do is they poop out the leftovers. The leftovers pile up kind of in a pile right next to them. They don't really push it out that far. And the next time they eat, they poop out again, and there's another little pile, and there's another little pile. And pretty soon they are surrounded by a pile of their own poop. So they live in that poop pile, and that's what forms the little rings on the coral itself. So those little rings that you guys see in the coral, and I've got some coral up at my desk here that you're more than welcome to hand around or come up and take a look at. But those little tiny rings and tubes are actually poop piles of the polyps that lived in the middle of that. The poop that they actually make is actually, and I, again, forgive my handwriting with this, but it's CaCO3, which is calcium carbonate, which is limestone. So they literally crap rocks. So they poop that stuff out, and it sediments around them, and it builds up around their body during their lifetime. So during their lifetime, they can be surrounded by their own little poop pile. They can't move. They're just stuck in place, and they just constantly eat and poop and live in that filth. Okay? Kind of interesting. Other interesting part here. When one polyp loves another polyp very much, they make baby polyps. So another polyp will be sitting over here, and through a process of just jetting sperm and egg into the water column, they will get each other pregnant. And when a polyp gets pregnant, what it does is it starts growing these little discs on the top of its mouth. And those little discs then, what they do is when they're big enough to do it, they break free and they go and they swim on their own. What's kind of odd about their shape is that they start taking this kind of shape. And I know it's kind of a crappy little thing, but they start growing like little surfaces down. And they float around in the water, and they start squishing and squeezing. And eventually, what you start seeing out of that is a shape that looks more like this. And hopefully, with your creative thought on this, when that gets big enough, which might take a month or two, this thing actually looks like this. Trying to do this, and hopefully you get the concept that their offspring are actually little tiny jellyfish. So these polyps reproduce, their kids are jellyfish, and they swim around in the ocean, really tiny, microscopic. They swim around until they reach full maturity, and then they will reproduce. And when they reproduce, when one jellyfish loves another jellyfish very much, inside their bell, inside their internal structure here, they form little discs. That's their kids. And their kids go off and float free, and I bet you can guess what's going to happen here. They start forming little rough surfaces on the top, which then turn into something that looks like this, which then turn into something that looks like that. So generally speaking, and again, I know this little, my drawing is not very good, but it's the best I can do. But you get the idea here that polyps give rise to something that doesn't look like them. They're called medusa. That's a medusa stage. And that's a jellyfish, what you would call a jellyfish. And then jellyfish will reproduce, and they will produce these little polyps. What's really weird about the whole thing, adding another layer of weirdness to this, is that the polyps, these little guys, will land in place on top of the little poop rings. And then they will start pooping on top of their grandparents and bury their old grandparents. And their grandparents will then die. This may be years later. Their grandparents will die being snuffed out basically by the poop of their grandchildren. And their grandchildren will just grow on that next layer on top. And that is why you get the concept that coral reefs grow throughout time. Okay? So some really kind of weird, interesting stuff about polyps and these little coral critters. Okay? Also, another little thing about them is that they will tend to, get rid of that, so there's a close-up of the polyp. They will tend to harbor little algae on their insides, so they will have different colors. So like this one has purple algae that grows inside of the body of the polyp, and this one has yellow, and different ones have different colors. So the color of the coral reef is actually set up by the algae that live inside of them, symbiotic relationship. And another cool kind of thing about it, here's some coral that you might look at a store or down in some tropical place. These are the poop rings then. So the polyp springs out of here at night and feeds with its little tentacles and everything, and then it poops out these patterns around in a big circle. So here's a polyp home, here's a polyp home, here's a polyp home, and then you get the overall idea of what coral is. Okay? So how does pH come into this whole thing? Well, carbon dioxide levels has been raising for the past 100 years or so. And most of that is due to industry and automotive usage, and it's pretty obvious where it's all coming from. We're burning fossil fuels, we're cutting down rainforests and burning stuff up. So there's a lot of carbon dioxide that's been spiked into the atmosphere. That in itself, maybe not such a terrible, terrible thing, but you combine that with another piece of information here, and we got a little bit more trouble. Carbon dioxide, and you can read this over here if you want to, but essentially I'm just going to have you focus over here on the carbon dioxide. The carbon dioxide is going to diffuse into the water. It just naturally soaks into ocean waters or lakes or streams or whatever it is. And it combines with that water, so you have CO2 plus the H2O, and it forms a carbonic acid, which releases hydrogen, which if you remember, the more hydrogen that you have, the lower pH that you have. And so what it does is every time that you have more carbon dioxide in the air, it gets soaked up by the ocean, combines with water, makes an acid, and releases hydrogen. Well, the damaging part of that hydrogen is used to absorb the carbonate from the coral. So remember the poop rings, the rock formations that they live on, is calcium carbonate. That's the base that they live on. And if you add acid to that situation, the acid will force this stuff apart into calcium ions and carbonate ions. And then the acid reacts with the carbonate and puts it into the stable ion right here. Okay? So ultimately, more hydrogen, lower pH, more hydrogen combines with the carbonate from the coral and dissolves this stuff. Literally turns it into a paste. And it turns into these two things, and then it pulls that out of there, and it stores this. And what it does to coral reefs then is low pHs literally turn coral reef formations into slimy, mucky, clay-type situations. So what that means, at 375 parts per million, that's carbon dioxide in the atmosphere. What ends up happening is that the coral reef is doing okay. It's not great, it's okay. And they're also implying here that temperature change also changes up how much carbon dioxide can get absorbed into the water. So if you warm the water temperature, more carbon dioxide can soak in. And if you recall, if I go back here one little step, more carbon dioxide ultimately means more hydrogen, which means lower pH, which means turning this stuff into goop and pulling it out and just saving it like that. So it just dissolves the coral. So again, the warmer the water temperature is, the more carbon dioxide gets in there. And at a warming of local water temperatures of 1 degree Celsius, 375 parts per million is what occurs in the water. And that has some effect, but not much. If you warm up the ocean temperatures by 2 degrees, you get up into this part per million, greater than 3 parts per million, or 3 degrees, sorry, you end up with more than 500 parts per million of carbon dioxide getting in the water, again, instantly changing into acid, and then that acid liquefies the reef. And this is what a reef ends up looking like when you acidify it with carbon dioxide. I hope that's making sense. So, some historic stuff here. Carbon dioxide levels started out in the 1850s in ocean water, being low levels. And in 2005, that's the most recent data on this one, somewhere around 500. And if you recall the last picture, 500 is getting to be very problematic for coral reefs. So that's in 2005, and people are like, well, hey, the corals are still doing okay. They're not. They're dying out at pretty phenomenal rates. And by 2100, the projected rates here are 926 parts per million of carbon dioxide in the water. Again, adding a lot of hydrogen to the water, lowering the pH. So if you look over here, same type of thing. The pH started out in 1850 as somewhere around 8.16. It has been dropping. And you remember, these are very small numbers of drops, but remember a factor of 10 is between like an 8 and a 7. So once we dip below a pH of 8, that seems to be the breaking point for most coral reefs. It liquefies and turns their calcium carbonate bases into ooze, and the polyps all die. So this is a problem, a serious problem. Here's where we've been at. This is pH levels, so here's your little scale over here. Remember I said the magic number is about 8. In 1995, these are our pH levels, and if we're still above that light bluish part, we're still doing okay. If I could get this to zoom in, and I found some other maps, but it's really not worth it. What's worth saying is that many places all over the world, the pH is dangerously close to 8, and by 2050, at our current rate of carbon dioxide expenditure, we're going to be somewhere in this green area, below 8. Below 8 means pretty much all coral reefs around the world die. And again, the ecology of that is that those coral reefs are not only homes to those really cool polyps in their story, but they provide that great, great nursery type of environment for the little fish. By 2095, you can see that we're way into the, way below an 8 level, and pretty much the point of no return. So I started this off with kind of the title, What Are We Doing? I'm not sure what we're doing. We need to do better as a culture, as a society, and scientific literacy is kind of the way to go on that. If you're not really 100% convinced, like, well, I really haven't heard much about that, it doesn't take much searching to find articles like this. This is from April 15th of last year, or of this year, I guess. Great Barrier Reef is about 98% dead at this point. So one of the largest ecosystems on this planet. In the last about 3 years, has faced 2 massive dying events in the past 2 years. So over the course of 3 years, it's almost gone, and it's getting wiped out. Ocean acidification is the culprit. Climate change is a secondary issue there because you're warming those water temps. And remember, warmer water temps mean more carbon dioxide gets absorbed, meaning more hydrogens, meaning lower pH. So it's a very, very somber look at how pH will be affecting you in your lifetime. I'm very, very selfish about my personal diving and my experiences, because my fear is that the science here is correct, and that by 2050, by the time I have grandkids and by the time you have adult kids, we're going to be looking at no more reefs around the world. So not a great lecture, not something uplifting, and isn't that neat and cool, but I think very, very valid. So there you have it. Hope you learned something about that, and hope you kind of could apply a couple of different concepts there about pH and how that affects things. Thanks for your time, and we'll see you some other time.